All right. Well, thank you very much for the invitation. In some sense, I feel a little bit like being back in graduate school with Mark and Miles being there and being in Warwick, not in the new building, but in the old building. It's a great pleasure to give this series of lectures. I want to begin by saying that this is joint work with Junwu Tu, my former student, currently at Shanghai Tech University, and partly with Kevin Costello. So half of this work is joined with Kevin as well. And it's very closely following ideas that were outlined by Kevin Costello 15 or 20 years ago. So let me begin easy and say what is our goal. Our goal is to start with a category, C, which should have some properties, which right now I'm going to swipe under the carpet, but it's things like maybe Calabi-Yau would be very important. And it's not going to be just a category, it's going to be something like a DG or A infinity category. So it has some enhancement, some extra data, but let's not worry about this for now. The main examples of such a category would be the category being the derived category of coherent sheaves of on a compact Calabi-Yau manifold, or the category being the Fukaya category of a symplectic manifold, or maybe another option would be some matrix factorization category of some potential on some quasi-projective variety. All of these categories, oops, sorry. This was bound to happen. All right. All of these categories will share the kind of properties that we want. And the goal out of this is to extract a whole slew of invariants that will be Gromov-Witten-like. So spoiler alert, already I can tell you that just the category will not be enough for the extraction of the Gromov-Witten invariants. We will need some extra data, but for now I want to begin by explaining what Gromov-Witten-like invariants are. So let me go back a little bit to Gromov-Witten theory, classical Gromov-Witten theory, and remind you about some work that was done in the early 2000s by Giventhal and Coates. So I don't know exactly who to attribute this. I'm not an expert on Gromov-Witten theory. I'm sure that Giventhal was the original motor for this. I have learned about this from some paper of Coates. So when you're doing Gromov-Witten theory, you start with some symplectic manifold X, maybe with some pseudo holomorphic structure that doesn't turn out to be very important. And you fix some class beta in the second homology of X, which I will think of as not being very important, so I will drop. It will become later on obvious what I mean, where this class is coming in. But for now, I'm going to drop this class beta from the importance of this thing. And the main output of classical Gromov-Witten theory are some invariants, which are usually written like this: tau I1 of alpha 1, tau I(n) of alpha n, Gn. These are some rational numbers. Where here alpha 1 up to alpha n are cohomology classes on X, maybe with rational coefficients, and I1 up to In are greater than or equal to 0, they're integers. And you should think of these as, these are insertions from X, and these are measuring psi class insertions. For those of you who know a little bit about Gromov-Witten theory, these are maybe sometimes called full descendant, full topological, full gravitational descendant invariant, something of that sort. So you get this huge list of invariants. Maybe I should have said G is a number greater than 0, which indexes what genus you're in, what genus you are. Now, it has been traditional to assemble these invariants together. So for a fixed G and N, people put these together into some kind of potential, and it's a map from sim n of something which I will call H plus into Q, where H plus will be my notation for the following strange space, UH double bracket U, where U is a variable of homological degree -2. I will use more of a topologist notation and use homology instead of cohomology everywhere. So my degrees will be homological, and so U has homological degree -2. Now, what do I mean by this? It's maybe confusing, but the idea is that if I had something like, I wanted to compute, let's say, tau 2 of alpha 1 and tau 3 of alpha 2 for some cohomology classes alpha 1 and alpha 2 on X, I would simply look at, this would be FJRW at some genus G, evaluated at U cubed alpha 1, U to the force alpha 2. This is simply, this 3 is 2 plus 1, and this 4 is 3 plus 1. So I need, for reasons that will become apparent later, I need one extra power of U here, but essentially the power of U just measures what what the psi class insertion I use. So and maybe there are some factorials which I'm omitting. I forget about this. All right. Now, for our purposes, it will be useful to take duals. And I will look at some element FGN X, which will be an element in some kind of completion, which I'm not going to tell you what exact completion this is, of sim n of some space called H minus, where H minus is now H adjoined U inverse. And the way I, so H minus is for me the dual of H plus via the very simple pairing where I decide that I take alpha U to the I, beta U to the J is equal to alpha beta. Remember that H is the, oh, I forgot to tell you that H is the cohomology of X. If I plus J equals to 1, and 0 otherwise. Of course, the cohomology of X, since X is compact, has a Poincaré duality pairing. And so H is self-dual, and I'm pairing U to the I with U to the J using this particular convention that I plus, if I only pair them when I and J is 1. And, so this is slightly different from the conventions that Giventhal would use. Giventhal would say take the residue pairing, where he would take here instead of 1, he would take -1. But I prefer to use the 1 for reasons that are kind of irrelevant at this moment. So this is still very much classical Gromov-Witten theory. This is called the dual potential, Gromov-Witten potential at G and N. And then the slightly more surprising thing that Giventhal and Coates do is they put together all the potentials at all the genera. That's not very surprising. So you define something called Fx, which is the following formal sum, Fgn x. And you introduce 2 formal variables, one to keep track of genus and one to keep track of the Euler characteristic, 2g minus 2 plus n. Here, again, the degree of this h bar is -2, and the degree of lambda is -2. All of those variables are nice and of fixed degree. And the slightly more strange thing that at first seems very bizarre is they define the total descendant potential called dx as this strange power series exp fx divided by h bar. And at first this seems very unmotivated. And this lives in some completed version of this polynomial ring, if you want, with coefficients in h minus. So somehow you should keep in mind that what I'm doing is something a little bit dual to what Giventhal and Coates would be doing. But even if you didn't follow all the details, the main thing is I have constructed some element in some kind of a symmetric algebra with 2 formal variables, h bar and lambda, which keep track of genus and Euler characteristic. And if I were to take the coefficients of this really complicated power series, after taking some kind of logarithm, I would be able to recover all the original invariants. So this is just a way to package all these guys. So all these guys can be recovered by knowing this one element dx of complicated symmetric algebra. So I recap here, H is the cohomology of the space X. H bar keeps track of genus. Lambda keeps track of Euler characteristic. And H minus is this H adjoined U inverse for another formal variable U, which keeps track of psi class insertions. And if you don't know what psi class insertions or Gromov-Witten theory is, you should not worry too much, because this will be just a motivation for what we're doing in the future. So the reason that Giventhal and Coates constructed this complicated expression is because it is expected, and in Gromov-Witten theory, it is not just expected, it's known, that this dx satisfies some differential equations, which I'm not going to write right now, but the point is that on this space, there will be some interesting operator some kind of operators, differential operators. And when you write down this element dx, it's not completely random in this symmetric algebra. It satisfies some rather complicated differential equation, which very seriously restricts what dx can be. Right? And now our goal moving forward is to do the same thing, but replace the space X by the category C. And it will need a little bit of extra data, and not so little bit, but you'll need some extra data. So let me try to explain in pedestrian terms what this extra data is. So the answer is that it is a splitting of the Hodge filtration. So if we were dealing, so I'm not going to yet tell you what that means for a category, but I will try to tell you what that means for an actual variety. So if the category C were the derived category of X for some Calabi-Yau manifold X, then we know that X has a Hodge filtration. So if you were to write down the Hodge diamond of X, like this, and you were to look at one of the rows of the Hodge diamond, the row itself would look something like this: HK0, HK minus 1, 1, up to H0K. And the Hodge filtration is the filtration, and maybe let me say this, the totality of this, if I were to put all of these together, at least dimension-wise, I would get something like HK of X derived. And the point is that HK derived has a filtration whose pieces look like this. In other words, HK0 is a sub. There is some bigger piece which is isomorphic to, which has a sub HK0 and the quotient HK minus 1, 1, and so on. So maybe let's do a very specific example. Let's try to do the case X equals an elliptic curve. In that case, the Hodge diamond looks like this. And the only place where an interesting Hodge filtration exists is here. This piece, if you look at it, it's H0 of omega 1. This piece is H1 of OX. So this Hodge filtration says that we have a short exact sequence that looks like this. H0 of omega 1 goes to H1 deram of X, goes to H1 of O. So we have this short exact sequence always. It's completely canonical. What a splitting of the Hodge filtration means is splitting this short exact sequence. In other words, finding something that a map that splits the surjective map from H1 de Rham to H1 of O. So in particular, if we think about X as C mod Z plus Z tau, maybe, for particular tau in the upper half plane, then I can think about the form dz on C that descends to the elliptic curve. And that's a natural element, a natural generator for H0 of omega 1. And that maps to something, some form that I would still call dz. And to split this Hodge filtration, I need to pick some other element of H1 de Rham, which will be the image of the generator of H1 of O. Both of these spaces are one-dimensional. This space is two-dimensional. And I just need to figure out where H1 of O goes. The standard choice that's made in Hodge theory, there is a completely standard choice, which is to take dz bar as my other element. So most people, when they think about H1 of O, almost automatically in the back of their mind say, okay, that's generated by dz bar. But that is actually a choice, which turns out to not be the correct choice for mirror symmetry. So for mirror symmetry, for reasons that will become clear later, the correct choice is something like, I think this is the right one. I need to check the signs. 1 over tau minus tau bar, dz bar minus dz. I will have to double check this, but this is something of that sort. So you can see that it's still a multiple of dz bar, but I've added a particular multiple of dz, which of course doesn't change the fact that it's a splitting. All right. Now, what happens for the Fukaya category? So you might ask, okay, well, when we define Gromov-Witten invariants, we just have a symplectic manifold. I don't need to make any choice of such a splitting. It's kind of, nobody told me when I defined Gromov-Witten theories that secretly I was defining it. I was making some choices in the background. So it turns out that the Fukaya category should have, and I'm not sure, I'm not a specialist in symplectic geometry, so I'm a little on shaky ground here, but from what I understand from people who work on this, the Fukaya category should have a canonical splitting. And intuitively, the reason that this is happening is because this is not a category over C. So this is not over some base field, but rather it's over the Novikov ring. So at least in the case when H2 is one-dimensional, what this should look like is that the Fukaya category really lives over a small punctured disk. And the main point is that somehow it also comes with this Dubrovin connection. And I'm speaking here about things that I don't know very well, but the main point is that using the monodromy of the Dubrovin connection, we can split the analog of the Hodge filtration. So you might ask, okay, well, this is a little bit of an asymmetry. You're saying that the Fukaya category has a canonical splitting, while the derived category does not. But mirror symmetry is supposed to interchange these. So you should say, well, this is not right. And where this statement fails is that mirror symmetry really holds only after the choice of a large complex structure limit point. There is some area of the moduli space. You need to choose where you are in the moduli space of complex structures. And the choice of where you are in the moduli space of complex structure around which large complex structure limit point, that determines a particular splitting of the Hodge filtration. So the whole moral of this thing is the following, that so the upshot is that we will attach an invariant similar to dx to a Calabi-Yau category C. And to be very precise, I will want it to be smooth and proper. If you don't know what this means for a category, it's just the analog for categories for saying that we're taking the derived category of a smooth and proper Calabi-Yau variety, not singular or non-proper. And a splitting of the non-commutative Hodge filtration. So I need to now make sense of all of these things. And the answer is the following. The role of the vector space H, which was before the singular cohomology of the symplectic manifold X, this now becomes the Hochschild homology of the category with some shift D. Here, this D is the Calabi-Yau dimension. What that means is that if I had a Calabi-Yau threefold, this D would be 3. And what is the splitting of the Hodge filtration? The splitting S of the Hodge filtration is a map from Hochschild homology of C to this thing called the negative cyclic homology of C. And this is a splitting. I will explain this in much greater detail once we talk a lot more about Hochschild and cyclic homology, but you should really think about this as HP omega Q in some incarnation, and this you should think about H derived. So I'm just trying to find a way to map all the Hodge groups, HP omega Q, into the Durham cohomology. Normally there is only a splitting, only a filtration with associated graded terms, this HP of omega Q, and I want to get a map that embeds it. All right. So this is the first half of the talk for today. I've just explained what our goal is. What is, maybe to finish, what is this D associated to a category C and the splitting S? It will live as before in some kind of completed version of H minus adjoined formal variables H bar and lambda. And this is completed and localized at H, so you can have still some negative powers of H. You saw this because I was exponentiating something divided by H bar. So this means some completion, which I'm hiding under the carpet exactly what that means. But it's some kind of polynomial, or rather Laurent series of H with coefficients in H minus, and H minus means as before H adjoined U inverse for this formal variable of degree 2, so it's degree minus 2. All right, so before we begin trying to construct this thing, I'm going to have to talk a little bit about Hochschild and cyclic homology and recall some stuff that we have. So let's begin with Hochschild homology. This is a construction that makes sense for a category, for a, let's say, DG or A infinity category. And if I feed into it the derived category of X, the answer is direct sum over all P plus Q equals to star HP of X omega Q. So what you should think about is that Hochschild cohomology, for when I feed into it the derived category of a variety, gives me the, oops, this is not correct. This is Q minus P equals to star, I apologize. So what you should think about is that this is graded from minus the dimension to plus the dimension. This is 0, and this is HHD, and this is HH minus D. So you're summing up the groups that appear on the verticals, not on the horizontals of the Hodge diamond. All right. This sounds like a nice thing. It can be defined as an Ext, but that's not the definition that I want to really take. I would really like to take a completely different definition, the one that makes more sense for a ring. So if A were a ring, in fact, maybe rather than ring, let's say K algebra over a field K, I could define the Hochschild chains C K of A as A to the tensor power K plus 1. So the tensor power is over the field. And there is a differential B, which goes from CK of A to CK minus 1 of A, which basically all that it needs to know is what is the multiplication. So it depends on the multiplication of A. Right? Now, this also makes sense for an A infinity algebra, and I apologize that I will have to say really quickly what an A infinity algebra is. If anybody doesn't know what an A infinity algebra is, you will have to basically look it up. So this also works for an A infinity algebra, where an A infinity algebra is very much like a K algebra, except that instead of just having one multiplication, which was going from A tensor A to A, that's what characterized the K algebra. This guy has more operations. So it has some operations called MK, which themselves take K inputs and go back to A, and they have degree 2 minus K. So this is a graded vector space plus operations MK like this, which satisfies some axiom, which I'm not going to tell you, but if we were only looking at the multiplication, they would look like saying that the multiplication is associative. And this, the Hochschild chain stays the same, but this operator B now depends on all the operations. So it's defined in a very similar way, and I'm not going to say much more about this. And the statement is that these C star of A with this differential B forms a chain complex. And I define the Hochschild homology of A as the homology of it. Okay. Now, one of the really nice things about Hochschild homology is the fact that, first of all, the Hochschild homology of a ring, if you want thought of as a category with only one object, is the same thing as the Hochschild homology of the category of, let's say, finitely generated A modules. So I told you that you could do the construction of Hochschild homology both for a ring and for a category. And it turns out that Hochschild homology does not distinguish between those two. So in particular, this also implies that Hochschild homology is Morita invariant. In other words, if I have two rings which are Morita equivalent, I get the same Hochschild homology. All right. This is a very nice property of Hochschild homology. So why is this of particular interest to us? Already we can get an important idea about how we're going to construct the invariants that we want. The idea is that the first idea is we will replace the category C by an A infinity algebra A such that C is equivalent to modules over A. Sorry, A modules. There's a lot of technology that is needed to say this, but morally it's going to be just fine. The whole construction that we will do will be Morita equivalent, Morita invariant. So there is no harm in replacing the whole big category of the derived category of X, which has billions of objects and all kinds of complicated morphisms, by only one A infinity algebra. Why is this possible? So as a side note, how? In theory, it's not hard at all. You find something called a generator of C, and by a theorem of Bondal-Vandenberg, such a generator always exists, at least for smooth projective varieties. And then take A to be the endomorphisms in DG in the DG category of which enhances the derived category of X of this generator. So this is now a DG algebra, which it's easy to prove that it's equivalent. The fact that E was a generator makes it easy to prove that this DG endomorphisms of E is Morita equivalent to the original category. And then the next step, this is a DG algebra in the sense that it has a differential endomultiplication. We don't really like that. It's infinite dimensional in general. Then we do a second process, which again, I'm not going to talk about. It's outside of the scope of these lectures, but you do something called homological perturbation, which gets rid of the differential, makes the algebra finite dimensional. It is now the X algebra of E, but produces higher multiplications. Okay. So this is not very important for us. This in the rest of the lectures, we will pretend that somebody else has done the work for us. It's not trivial work, and in fact, it's highly difficult work, but I'm going to state some theorems here for elliptic curves. Such A is constructed by Polishchuk. Explicitly. So he writes down completely for you all the higher multiplications MK. And the second theorem by Junwu Tu is for Calabi-Yau hypersurfaces. We have an algorithm. To write down all the higher multiplications of such A. This is Junwu Tu's separate work. Okay, so at least for things like elliptic curves and quintics, we can not only, so we know completely abstractly that such an algebra always exists. The trick is to write it down explicitly. And for elliptic curves, we have something down by written down by Polishchuk, and for Calabi-Yau hypersurfaces in general, we have such a thing by work of Junwu Tu. Now, there is one more little thing which is actually not so little in deciding what we want for our input, and that is we want A to be something called cyclic. And this is what I will mean by cyclic. I will want A to have a pairing which is non-degenerate. Remember that A was made to be finite dimensional at one of these stages when we did homological perturbation. So it can have a non-degenerate pairing. And
let me quickly interrupt you. So there was a question about 7 minutes ago that I missed, and it was, the question was, are you thinking to have homological units?
Yes, I want my algebra to have homological units. And the point is, even if it doesn't, if your algebra doesn't have homological units, you can formally add them in the beginning. But the constructions we will have for this A-infinity algebras A will automatically have units. This is not, I think the problem of the existence of homological units is more of an issue in the Fukaya category. But the way we will take the input A, the way it will be fed into the next stage of the construction, the next stage of the construction actually doesn't care about whether A is unital or not. So we're fine either way. Okay? I hope I've answered that one.
Thank you. So
let me now state the definition of what cyclic means. I want my algebra A to have a pairing that's non-degenerate and such that the following property holds: mk of x1 up to xk paired with xk plus 1 is graded cyclically invariant. In other words, up to a sign, So there's going to be some sign here, which I'm not going to try to write down. This is equal to mk of xk plus 1, x1, and so on, xk minus 1, and then xk. So if I take the operation mk and pair it with one more element, the resulting tensor is cyclically invariant. This is the way you should think about this condition is this is the Calabi-Yau condition. And the reason for this is because if you remember, my algebra A was, at least on the face of it, it was just x star of EE. And if X is Calabi-Yau, I know that there is a Serre duality pairing X star EE, tensor X star EE, maybe with a shift by D or something like this, going to the ground field. Okay. Right? Normally, we would have here tensor omega, but because X is Calabi-Yau, this tensor with omega goes away. So this is the pairing, and we know that because of its very construction, at least for the usual multiplication, Yoneda multiplication on X, this cyclicity condition holds. Another way of thinking about this condition, of this cyclicity condition, so cyclic is a higher analog of saying that we have a Frobenius algebra, which is exactly saying that you have an algebra with a pairing such that xy paired with z equals to zx paired with y. This is a cyclicity condition. So this is when instead of an A infinity algebra, you have a full, if instead of an A infinity algebra, which is a full structure, you only have one multiplication. And people probably know that Frobenius algebras are very closely related to two-dimensional topological field series. So now this allows me to introduce the next statement, which is the big shot statement that really should puzzle you a lot. And that is a big theorem due to Kontsevich-Soibelman, and Costello, which says, given a cyclic A infinity algebra A, there exists a positive boundary. I'm going to explain all these terms. Two-dimensional extended TFT. From now on, I'm going to drop the word extended and just mean, say, TFT, given by maps rho A from chains on M, G, K, L framed with a shift here, which I'm going to ignore for now, with values in HOM, L tensor K, L tensor L, with target L, which is by definition the Hochschild chain complex of A, shifted by D. Here, the Calabi-Yau dimension is D. So this is a big theorem, and I want us to spend maybe 5 minutes before the end of today's lecture to discuss the meaning of this theorem. What this theorem says is the following. Let's say you start with a cyclic Calabi-Yau A infinity algebra A. Let's pretend for a second, let's go back to our basics and pretend that we were just having a Frobenius algebra. So instead, let's simplify our life considerably, and instead of having a cyclic A infinity algebra, let's pretend that we have just a an ordinary Frobenius algebra.
Quick, there was another question, which is what are the assumptions for K and L? Is it K greater equal 1 and L greater equal to 0?
Yes, exactly. That is correct. So, okay, let me try to explain. Positive boundary means exactly what you just said. Means K greater than or equal to 1, L greater than or equal to 0. So, okay, so maybe perhaps the audience knows a little bit more, and I don't need to go into the very simplest case. The main point is this: what's a field theory? A field theory is something that associates to manifolds morphisms in some category. So a typical picture that you might see in a field theory is something like this, and to this you associate something which is a homomorphism from, let's say, V tensor 2 to V. I hope maybe people have seen something of this sort, that you associate this. I'm taking here a pair of pants, and to a pair of pants I associate a map between two copies of a vector space and one copy of the vector space, because I think of this as having two input boundary circles and one output boundary circle. So I get a map from two copies of a fixed vector space V to another vector space V. This V is called the target of the field theory. Now, this is a purely topological field theory in which I only think about this surface as a topological manifold. But sometimes people like to put more structure on it. So the most complicated thing you could do is you could take a conformal field theory, which would mean that I think about associating a particular map of this sort to a surface, but with a conformal structure. That would be an extremely rich theory. So that would mean that I would need to have something like MGKL. I would need to get a map from rho A from MGKL to some homomorphisms, L tensor K, L tensor L. So I should have explained that this K and L is the number of, it refers to the number of inputs and outputs of my Riemann surface, if you want. Now, I'm not doing that full thing, which is complicated, but I'm doing something in between the full topological and full conformal. Namely, I'm doing something which used to be called topological conformal, but then it was realized that it's the same thing as an extended TFT, which is I'm replacing this space of all conformal structures on a Riemann surface by the space here of chains on it, singular chains. So somehow I'm capturing something about the topology of the moduli space of conformal structures on Riemann surfaces of a particular type. So now let me try to say again what these notations mean. MGKL means the moduli space of Riemann surfaces with K plus L punctures genus G. K of these punctures are, K are designated inputs. L are designated as outputs. But I don't want exactly this. This would be a very nice algebraic variety. We know everything, well, not everything, but we know a lot about it. I want to decorate it a little bit more. Namely, I put a framing. And what the framing means is plus, you can say this in many different ways. One way you could say is you could take a real ray in the tangent space of each marked point, or a framing of a small neighborhood of each marked point. It doesn't really matter very much how you set it up, but the moral of this is that the pictures that you're having will, instead of looking like this, so some particular Riemann surface with inputs and outputs, but moreover, on each boundary circle, I choose a point. So pretend that I am choosing a marked point on each boundary circle. So instead of having a puncture, I actually cut out a tiny disk. And on the boundary of that disk, I choose a point. So of course, it's easy to see that this maps down to the ordinary MGKL. And this is a fibration with fiber S1 to the power K plus L. All that I'm doing is for every marked surface, I choose a framing. One other way of saying is I pick an isomorphism of a collar around each marked point with a standard punctured disk in C. Homotopically, up to homotopy, this is the same thing as an S1 choice. All right, now let's go back to the theorem that we had here. This moduli space is some topological space. This C star means singular chains. And what I'm saying here is that I'm a 2D extended TFT gives me a way to associate to every chain in this moduli space a particular homomorphism between these particular spaces, where L is this the Hochschild chains of A with some shift. Of course, just saying that I give you these maps doesn't mean anything, but the important thing is, because I have chosen a framing, I can glue together Riemann surfaces. And so I have interesting maps that look like this: MGKL framed cross MG, maybe LM framed, going to MG prime, going to MG plus G prime KM framed, in which I sew the outputs of this, of each Riemann surface from here to the inputs of the next one. And what I want is that it certainly induces a map that looks like this on singular chains. And I want that to correspond to composition under the action of rho A. This is exactly what saying that I have a field theory means. The crucial thing that I want to say is this observation that was made, that we only can construct this rho A to be a positive boundary TFT. There's a real substantial reason why we can't possibly do this in general, is because if we could extend to the case k equals to 0, the setting where we allow 0 inputs, we would be forced L to be finite dimensional. This is a very standard argument in field theories, that if you somehow allow yourself this kind of operator and this kind of operator, so the tube is 2 inputs and the tube is 2 outputs, the target of your field theory must be finite dimensional. But of course, we kind of know that this must be the full Hochschild chains of an algebra, and that's very infinite dimensional no matter what you do. So the way this is fixed in the theorem, so we don't get a false theorem, is we only are able to define this for positive number of inputs. This will be a crucial step that we will have to overcome in the future parts of the construction. All right, I think maybe this is a natural place to stop. I have not yet said anything about how the invariants are constructed. Next time I'm going to try to begin with a sketch of how the invariants are constructed, skipping many steps, but using this topological field theory that I've explained today. Let me stop here.